All right, so I'm going to try to record this for you here with this up and looking at the graph here. Now, let me see. Will it let me zoom in? No. All right, so a little bit hard to see the graph, but that's okay. Let's see. If I make it full size, I'll move the video over here. All right, yeah, we'll just do that. So we plotted the data. We've got this fit line. So now we want to talk about the evaluation of data, and I'll try to write kind of big here. My Sharpies are all dead, so actually I do have this nice red marker. This might work well. So evaluation of data here, right? Yeah, that's be good. All right, so again, we talked about the purpose of this lab being to determine the relationship between the force applied to a spring and how far it stretches, right? So we found that the stretch distance was directly proportional to the force applied. So the more force, the farther the stretch length. Now, normally we'd want the force on the x-axis here because that's the thing we controlled, and we measured how far the spring stretched. But the way that the equation ends up coming out, we want force to be on the vertical axis there. All right. So the equation, our experimental equation, I'll write it next to this to give myself some, well, yeah, experimental equation. So your lab evaluation of data, it'll start with the sentence explaining this, right? So this is going to be in order you should write the evaluation of your data in your lab. So the stretch distance was directly proportional to the spring, the force applied to the spring. The experimental equation is as follows. Ends up being force equals, now I'm writing this up for my lab here, right? I'm going to do 2 sig figs because if you look at the raw data for this, right, my spring lengths, I only did 2 sig figs. It was 4.0, 5.0, and so on. So my slope of my line shouldn't be any more precise than that. Logger Pro will always give you 4 sig figs no matter what you put in, right? So anyhow, we're just going to go 15 newtons per meter times the stretch length. Our y-intercept here is fairly significant, and we'll talk a little bit about that. 8-9 newtons, so 2 sig figs. So let's talk about the slope and y-intercept now. So once you give the experimental equation, we want to talk about the slope and y-intercept. So the y-intercept here is the force that appears to be applied when the spring is not stretching. So it's the force when stretch, or the stretch, well in this case it's force, when stretch, STRE, equals 0 meters, right? Well, looks like there's a force being applied even though the spring is just hanging there. So what could cause that? Well, it could have been that the ruler was just shifted, like maybe that red thing, that little red thing on there was not exactly at 50 centimeters when you started, or maybe the spring itself caused a little, if its own mass caused it to stretch a little bit. Again, it's fairly low. It's fairly close to 0. Some of you, it was fairly close to 0. The general rule of thumb is if it's less than 10% of the maximum Y value, which this actually is. So our maximum Y value is like 0.17. 10% of that, 1.7, sorry, 10% of that would be 0.17. And this is less than that. It's more like 7% of the max value. But anyway, so this really should be 0, right? It has no specific meaning. It should be 0. It should be 0 newtons. If there's no force, it shouldn't be stretched. So again, either the force of gravity acting on the spring itself is stretching it a little bit, or your initial 0 location was not that accurate. Now the slope here is very important. All right, we're going to see in class when we compare the slope between, now this spring, this is like one of the middle springs, right? It wasn't the real loose one. It wasn't the real strong one. It was kind of in the middle, all right? And what we'll find is the real weak spring, its slope was like 2.1 or 2.5 newtons per meter, all right? The real strong one is 27 newtons for every meter. So what the heck does that mean? Well, basically, it's force per stretch per meter of stretch length. So if you had a really long version of this spring, it would take 15 newtons of force to stretch this spring 1 meter. Now, clearly, if I stretch a spring much farther than even this, it's gonna get bent out of shape. So usually we scale this down to centimeters or fractions of a meter, right? 150 newtons per meter, that would be 0.15 newtons per centimeter. So this has a name, all right? It's the amount of force to stretch it 1 meter. So amount of force to stretch 1 meter. However, that's not really a possible thing. So the stronger the spring, the bigger the slope of this line. The weaker the spring, the lower the slope of this line. So what we would call it is, it's kind of a rating of spring strength. It's a rating of spring strength. And it actually gets a different name called spring constant. All right? So for this spring, that slope of the line, no matter who measures it, is going to be the same. It's going to be a constant. And it has a symbol. We use a lowercase k. A lowercase k. Lowercase k we use for a constant in more than one location. So you got to be careful with that. Spring constant, lowercase k, the units are newtons per meter. All right? So that brings us, so that kind of wraps up the evaluation of data, right? So you'd say the stretch length is proportional to the force. Experimental equation is this. You got to make sure you put units on stuff. This often can just go to 0, right? It's often small enough that can just go to 0. Your slope is what goes into here, not this one, unless you did this spring. Your y-intercept we talked about, the slope we talked about. So you got to put these notes into sentences, all right? Into sentences in evaluation of data. All right, I'm going to grade this lab a little bit stronger, okay, a little more carefully. So please, I'm going to make it due next week, Tuesday, Wednesday. All right, probably Wednesday officially due. So bring it to me. Bring it to me Monday or Tuesday, and I can help you look at it. Now, the next thing here is the final thing we have to do is talk about the general equation. So remember, the general equation is the equation that ends up going on the reference table, right? We just take our experimental equation and we replace any numbers in it with the variables that we defined them as. So the general equation here ends up being f equals lowercase k times x. And this is a law of physics. This is called Hooke's law. All right? And it really only applies for what we call linear springs. Hooke's law, and technically it's for linear springs. Sometimes they also call this ideal springs, kind of like the ideal gas law. So not all springs behave linearly. In fact, rubber bands will sometimes not behave linearly, right? It'll be related to kx squared or the square root of x. It won't be directly proportional to x sometimes. Sometimes when a spring has been damaged, it won't behave linearly. Sometimes we call a spring, it's kind of a funny word, Hookean. Hookean, if it obeys Hooke's law. A Hookean spring. So that's Hookean. A Hookean spring obeys Hooke's law. Kind of a funny thing. One last thing we got to do here. So the lab pretty much ends here. All right? The lab pretty much ends here. That generally, so in your conclusion, again, you'll say the length the spring stretched was, proportional to the force applied. We derive this new general equation. The slope of the line is spring constant. This is a new concept. It's a rating of the spring strength. This equation is called Hooke's law. Hooke, actually, he's a funny guy to look up, actually, an image of. Robert Hooke. He's got a sweet hairdo in a lot of the images of him. One of those big poofadors. He did crazy stuff. Lots of different stuff. Not just springs. That's like a side note. He had these crazy drawings that he developed of the features of animals and plants and wildlife. So really kind of a neat, well-rounded guy. Look at all the different things he's involved in now. There's one really great picture of him that I've seen over the years with crazy hair. But yeah, there we go. That's a good one. No, that's Huggins. Oh, anyway, kind of looks like De La Salle in that image, doesn't he? Yeah. Classic. These pictures of the big hair. Love it. Anyway, there we go. There's that. One last thing to do here and talk about is tie this together with energy. My lights just turned off. Hold on one second. All right. One last thing to do is to tie this all in with energy, and that's going to go back to the graph. So, how does this relate to energy? Force and X, and it was linear. All right. Well, it turns out the amount of energy stored in a spring is equal to the area under the curve. So this ends up being equivalent. The area under the curve ends up being equal to the change in the spring potential energy as it's stretched. So if you stretch a spring some distance x, right, and it's held in place with some force F, you've stored energy, right? So the farther you stretch it, right, this line goes up farther. So if you only stretched it this far, it'd be the area of this triangle. The farther you stretch it, the more the energy stores up. So this is pretty cool here. The amount of energy stored in a spring, we can derive a formula for it from the area under the curve. So this is very important. This is a definition here. Area under force versus distance or position equals change in energy, or what we call work. All right? Change in energy or work. All right, so this is a really important. I'm going to shoot another video later on talking more about this, but area under force versus position is change in energy or work. So the amount of energy stored in the spring, the change in potential energy of spring is, you can call that delta X here if you want, is equal to 1/2 base times height, which is 1/2 of the base, which is delta X. The height of this triangle is whatever force it takes to hold it in place. I'm going to call this Fs. Oh, I should have called that back here in the general equation. I should have called that spring force. Call it spring force. That's our spring constant. And that's our stretch length. All right? Anyway, force of the spring. Force required to hold it in place. But what we do here is we put in Kx for Fs. And what the delta, that doesn't really need to be there. It's just, this is X, the length of this, right? So maybe I shouldn't have included the delta there. So what you get is change in spring energy, or the spring energy stored in the spring, is 1/2 Kx squared, right? Because it's x times kx. That becomes x squared, and we usually put the k there. So that's the derivation of the spring energy formula for you. All right? All right. This part doesn't need to go in the lab, but you do need to know that. So make sure you think about that. We can actually apply that to gravity as well, right? So if you make a force of gravity graph, right? Force of gravity versus height off the ground. So imagine you lift a ball off the ground, right? And you move it some height. Well, as you lift it up, the force of gravity stays constant, right? It doesn't change as you lift it higher off the ground. Actually, technically it does, but not when we're close to the planet, not for the problems we're doing here. All right. So the area under the graph here ends up being, okay, whatever the force of gravity is, multiplied by however high you've lifted off the ground. So the change in gravitational energy ends up being the force of gravity times the height, or mgh. So again, that equals work or change in energy, the area under the force versus distance. And the distance can be height, it can be radius, it can be x, y, just any length measurement. All right, I'm going to stop that there, put it all together.